Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is basic ladder logic. Our objective today is to take an introductory look at ladder logic diagrams, the principal means electrically controlled systems use to document and convey not only connection of individual devices making up the system, but also the function of that system. Additionally, this lecture includes coverage of a handy configuration called a holding circuit. Recall during the Introduction to Electrically Controlled Systems lecture, available at the Big Bad Tech channel, we briefly discussed ladder logic diagrams. Ladder logic diagrams flatten out traditional schematics and make connection and function easily readable and apparent to those practiced in their use. Ladder logic is a new language, and quite like learning a new language, necessitates repeated exposure and practice. Feel free to pause, rewind, and review this lecture as needed, since it establishes important grammatical rules and applies it to common industrial applications. Consider traditional schematics used to draw a DC source in a series circuit with a momentary normally open push button and a solenoid of a solenoid-operated hydraulic valve. When push button 1 is closed, it completes a path from X1 through solenoid A to X2. The hydraulic schematic indicates that when solenoid A is energized, it would shift to the straight-through position and the cylinder would extend to the limits of travel. When released, the momentary normally open push button 1 spring return returns it to its deactivated open state. Solenoid A would be de-energized and the spring offset directional control valve would return the valve to the cross-connect position and the single-acting cylinder would retract due to the spring inside the rod end. This is effective and understandable. However, the use of traditional schematics would be very cumbersome for a complicated circuit. For this reason, pilot schematics are ordinarily drawn using something called ladder logic. Tough luck compressing the hydraulic schematic. A ladder logic diagram basically flattens out a traditional schematic into readable lines, where each line is a path from one terminal of the source to the other. It is readily apparent that in order to complete a conductive path from the hot or high side X1 through solenoid A to the low or neutral side X2, one must close push button 1. The low voltage output of the control transformer, or the power supply in the case of a DC control voltage, X1 and X2 are now represented as the left and right side of vertical upright rails of a ladder, and the conductive path from X1 to X2 is represented as a rung on that ladder. A ladder logic diagram for an electrically controlled system incorporating motors and magnetic contactors is almost identical. One would show a control transformer output used to step down primary voltage between any two phases to pilot voltage as upright vertical rails, X1 being the left and X2 being the right. If one was to draw both the pilot and primary schematics using the same diagram, ordinarily the pilot low voltage ladder logic diagram is drawn in thin lines, and the primary high voltage schematic is drawn in thick lines. I tend to find this method a little busy and confusing, so I ordinarily draw the pilot and primary schematics separately. Realize the primary and pilot schematics are linked via magnetic or mechanical means. The pilot signal is low voltage, low current, low power electricity, entirely separate and electrically isolated from the high voltage, high current, high power primary input and must always remain so. The only interaction between the pilot and primary electrical signals is via magnetic or mechanical means. Examples would be the transformer, the contactor coil, and the overload relay. They are electrically isolated for a reason, and the primary reason is safety. Pilot signals for modern electrically controlled systems are ordinarily 120 volts AC or 24 volts DC as representative examples, with a notable progressive movement favoring 24 volts DC. It is plainly evident that these levels of electricity are not nearly as dangerous as high voltage electricity used to deliver power to an industrial motor, nor nearly as dirty as oil-based pilot signals for a hydraulic system. That's the point. The customary use of low voltage, low current, low power electrical pilot signals offer a degree of ease, safety, and isolation for operators and technicians assigned to install, maintain, troubleshoot, upgrade, operate, and repair electrically controlled systems. Let me simplify our ladder logic diagram ever so slightly. Again, this ladder logic diagram flattens out the traditional schematic, and it makes readily apparent that in order to complete a conductive path from the hot or high side X1 through coil F to the lower neutral side X2, one must close the start push button. When the F coil is energized by the pilot signal, the F contactor closes the three primary contacts. Note this pilot schematic includes normally closed overload elements in series with the normally open start push button and the F coil. Consider the significance of this arrangement. Consider an operator pressing the normally open start push button, which energizes the F coil, which closes the primary F contactor. The motor is energized and begins rotating. However, due to misalignment of the shaft or a bad bearing, the rotor locks up. The locked rotor condition begets unusually high primary current, which heats up the stator windings, at which point the overload element signals the normally closed overload contact to open. Despite the operator maintaining closure of the normally open start push button, the F coil de-energizes because there is no path from X1 to X2. The de-energized F coil means the F primary contacts open, and the motor de-energizes until such time the overloads are given a chance to cool, at which time the normally closed overload contact would reclose. The normally closed nature of the overload contact disallows operation of this system until it is safe to do so. Cool or not cool? Trick question. This is totally cool. The ladder logic diagram illustrates this function in a single line. The only way you can turn this motor on is if you're pressing the start push button and the overloads aren't overheated. Which begs the question, how do you turn on a motor or extend a cylinder at the touch of a button? I don't know about you, but standing around holding down a momentary normally open push button all day to run a stupid fan or dumb pump isn't one of the things I consider a rewarding priority. Before we open up this barrel of rage-infected bunkies, though, let's lay down some ground rules about ladder logic diagrams. First and foremost, if one needs to ground reference the output of the control transformer or DC power supply, one customarily does so on the right-hand side of the pilot ladder logic diagram, in this case the right-hand X2 upright rail. This ensures that overcurrent protection devices like fuses and circuit breakers function as intended and ensures that an errant connection to ground does not inadvertently start a hydraulic system or motor. This is to suggest that ladder logic diagrams prefer high-side switching arrangements. I'll come back to clarify this point in a moment. Ladder logic diagrams only show pilot-rated electrically active components like switches, pilot lamps, control relays, contactor coils, and the solenoids of solenoid-operated directional control valves. Primary devices like hydraulic components or contactors aren't included. These devices would appear in the primary hydraulic or electrical schematic. Ladder logic diagrams illustrate the connection of pilot devices only. Input devices like switches are ordinarily drawn on the left side of a rung. The one exception to this rule is the normally closed overload contacts, which are a form of input placed on the extreme right. Output devices like coils are electrical loads. When a rung's input devices allow closure from one upright to the other, the load is energized. Outputs normally go on the right. A series connection of two normally open switches means both push button 1 and push button 2 must be simultaneously closed to energize lamp A. This is the logical AND operator, and its function is readily apparent as illustrated by the ladder logic diagram. A parallel connection of two normally open switches means either push button 3 or push button 4 must be closed, or both together to energize lamp B. This is the logical OR operator, and its function is readily apparent as illustrated by the ladder logic diagram. Input and output devices are ordinarily only featured in the horizontal rungs. The vertical uprights are power connections only. The one exception to this rule I've occasionally observed is the placement of fuses and main shutoffs in the vertical uprights. The fuses aren't really elements in the ladder logic, but rather serve to protect the pilot circuit from short circuit events. A rung in a ladder logic diagram is never composed of input devices only. If an operator closed push button 5, the rung would experience a short circuit from X1 to X2 with no opposition to current flow. The fuse in the vertical upright would blow, and your lab instructor would issue you an express ticket to push-up land if you were to ever do something stupid like this. This is all sorts of wrong. This is to suggest the maxim that all rungs must contain one electrical load. Similarly, load devices aren't ordinarily directly connected from one vertical upright to the next, unless you want that device continually energized. Lamp C would always be energized. What's the logic in that? Our diagram and list is getting a little bit long, so let's go ahead and give ourselves some room. Next, loads are never placed in series with one another. Load devices in ladder logic diagrams are designed to operate at full pilot voltage. Assuming equal resistance of lamp D and E, if push button 6 was closed, we would see 12 volts across lamp D and the other 12 volts across lamp E, assuming 24 volts DC pilot voltage. This is wrong. Both lamps would be dim if they operate at all. This is to suggest the maxim one load per rung. Load devices must be placed in parallel with one another if they are to be simultaneously energized. The closure of push button 7 would energize both lamp F and lamp G with a full 24 volts DC they are intended to operate at. Ladder logic diagrams must be properly documented, referenced, and feature properly numbered rungs and wires and fully identified components, terminals, and contacts. We'll discuss documentation, rung numbering, wire numbering, component identification, and referencing in a later lecture. Finally, and this may sound like nonsense to you right now, but you'll appreciate this advice later. All internal logical loads ordinarily appear in the top half of a ladder logic diagram, and all external output loads appear in the bottom half. An example might be an electrically controlled system using a control relay, a timer, a counter, a solenoid, and a pilot lamp. The control relay, counter, and timer, since they perform internal logic functions, would be in the top half of the ladder logic diagram, and the solenoid and pilot lamp, since they are observable external outputs, would appear in the bottom half. Again, this will make more sense as we extend our analysis into increasingly complicated electrically controlled systems.